So, like I said on Friday, right, is that the long division and synthetic division are both really useful tools to help us factor things we otherwise wouldn't be able to factor, right? When we've been factoring in the past, right, quadratics, we can pretty much factor any quadratic that's thrown our way if it is in fact factorable, right? But then if we start talking about cubics or quartics and stuff like that, then we have to kind of use those other strategies we've been talking about, where it's like factoring by grouping maybe, or GCF, right? Or if we can make it look like a quadratic, then we can factor it like a quadratic kind of thing. But even still, with all those tools, right, we run across things we couldn't factor using those, but they still might be factorable. In fact, we saw, right, some things on Friday where they didn't follow factor by grouping or anything of those other tools that we had, but we could still factor things if we knew what their factors were in the first place, right? But of course, knowing what a factor is for a problem, it's kind of like, well, then why do we need to factor if we already know the answer kind of thing, right? And so, and of course, there's an infinite number of possibilities that we could kind of come up with about how to about factoring. An infinite number of possible factors for something. So we just are supposed to guess, right? Well, yes, essentially, okay. But the good news is we have this thing called the rational zero test, which takes our infinite list of possible factors, right? And this will give us a list of all possible, so it's not going to tell us which ones are and which ones are not factors, but it'll give us all the possible rational zeros for a given polynomial. Okay, all possible rational zeros for a given polynomial. And so, again, this is not going to be exhaustive either, right? Because there are going to be polynomials who maybe don't have any, or that don't have any rational zeros, right? Rational numbers are numbers that can be written in the form a over b, where a and b are both integers, right? So, for example, this excludes something like the square root of 2, right? Square root of 2 it cannot be written in the form a over b, where a and b are both integers, right? Root 2 is its decimal, for example, goes on forever, and it never repeats regularly, and doesn't end either, right? So, anyway, but it still helps us out a little bit, right? It expands our capabilities just a little bit more. So we'll ask the question then: what are the possible rational zeros for, and then we'll look at an example here, and we'll say x cubed plus 2x squared minus 4x minus 8. So again, our question is not to solve this thing, not to solve it. We just want to come up with the possible rational zeros. In other words, we're going to use this rational roots test. We're going to use this as kind of our example here, okay, to start out. So, in our polynomial, we're going to identify two numbers, two coefficients, right? The first number we want to identify is our constant term, and we're going to label that or describe that as P, okay, capital P, right? And then we're also going to describe also going to look at our lead coefficient. So we need to make sure that our polynomial is in the degree from greatest to least, right? And so the lead coefficient is the number in front of the greatest term, and that we're going to call Q. And in this case, right, it's a 1 because there's no number written there, but we assume a 1 in front of our variable there. Okay? And so with these two numbers, right, and using what we know about how things have to factor and multiply together, we can understand, we can, surmise here that the possible zeros will be of this form: factors of P over the factors of Q. And again, just to help us remember this, P is the constant term, Q is the lead coefficient. Okay? So what are the factors of 8 or -8? In this case, right? What are the factors of 8? What divides 8 evenly? Okay, 1, 2, 4, 8. And of course, plus or minus 1, plus or minus 2, plus or minus 4, plus or minus 8, right? Because both positive and -1 divide 8 evenly. Both positive -2, positive -4, positive -8. Okay. All right. What about the factors of Q? Well, just 1, right? Or positive or -1. That divides. Okay. And you'll notice to put this in the specific order here where the factors of P are over the factors of Q. In other words, our zeros, okay, the possible rational zeros for this polynomial will be in this format. Okay, so then let me take this kind of organizational tool that we use here, and I'll list all the possible rational zeros. Okay, so the first grouping here would be what? 1 over 1, right? So we're going to have plus or minus 1 over 1, which is just 1. Plus or minus 2 over 1, 2. Plus or minus 4 over 1, 4. Plus or minus 8 over 1, 8. And we could also do plus or minus 1 over -1, but then it just becomes minus plus, which is really just the same thing. Plus or minus 2 over -1, and again, it'd be minus plus, but it'd be the same. It's still just, both positive 2 and -2. So, I mean, we don't have to, go through all positive ones and all negative ones there. It's just that's the exhaustive list right there. Okay? And so that's our answer, right? That's what we're looking for here. What are the possible rational zeros for that polynomial? It'll only be these possible 8 numbers, right? According to the rational zeros test. This identifies those 8 rational zeros, okay? If there are rational zeros for this, it will only be among this group of 8 possible zeros. Okay? So let's find the actual rational zeros, right? What are the rational zeros for x cubed plus 2x squared minus 4x minus 8? So in other words, if we're trying to find the rational zeros, we're going to set this thing equal to 0, right, and solve this. Okay? So what strategy might we use here? We've got a list of possible rational zeros. We have, a polynomial here, right? What strategies might work here? Okay, substitution. I would say I don't think substitution is going to quite work, but yes, grouping should work. The problem with substitution here is that we have too many terms. Substitution we need 3 terms because a quadratic typically has 3 terms. But yes, grouping would work. Aha! So let's group here. So I'll group together the first 2 terms. So we'll factor out an x squared, and we're left with x plus 2. And what can I factor from the second group of terms there? Good, a -2. Yeah, we want to factor out a -2 there. And so we're left with -2 and then 2x. We don't want to factor out -2, my bad. Well, I mean, a -2 works, but bigger than that, a 4, right? Yeah, that's okay. Yeah, -4, that'll be better. You could do a 2, but then you would need to factor out, oops, and now I have a 2. All right, I just messed the whole thing up. I'm just going to rewrite it. Minus 4x plus 2, like that. There we go. Okay. All right, taking -4 out of -4x leaves you with a positive x, and -4 taken out of a -8, or factored out of -8 leaves you a positive 2. And so we can take out the x plus 2, and the x squared minus 4 equals 0. And then x plus 2 equals 0, x squared minus 4 equals 0. So x is -2, and x equals plus or minus 2. So you can see a double root, I guess, at that -2. So x equals 2 and -2 are our 2 rational zeros there. Okay, the -2, I guess you can say, occurs twice, right? But anyway. Yes, okay. So this one grouped. That was nice. Okay, that was nice. All right. Questions on any of that? All righty. Let's take a look at another one. And you can also see, by the way, before I move on here, you can see, right, these two zeros that we got, they are in our list, aren't they? Right there, plus or minus 2. Okay. All right, so let's take a look at another one. Let's find the rational roots of, and now we'll do x to the 4th plus 2x cubed plus x squared plus 8x minus 12. Bless you. Okay, so let's see here. We got to list our possible zeros. So, well, I'm going to identify our p's and q's here first. So p is 12, or negative 12 if you like. Q, 1. Okay, and so that makes our possible zeros then, they'll be in the form p over q. Or the factors of p over the factors of q. So let's think about the factors of p, right? That's plus or minus 1, 2, 3, 4, 6, and 12. All over the factors of q, well, that's easy. It's plus or minus 1. Okay? And so since q is just 1, then it's really just these are our list of factors. It's either positive or negative 1, positive or negative 2, positive or negative 3, positive or negative 4, positive or negative 6, positive or negative 12. Okay. So we actually want to see which one of these work, though. Okay. So could we factor a GCF out here? Yeah, no, there's no GCF factor. Could we factor by grouping? Well, I mean, you could group, but there's an odd number of terms, and so even if you do kind of group things, you're going to have two different sized groups, and the leftovers won't be the same thing. So yeah, factor by grouping doesn't quite work here for this polynomial. We can't really make it look like a quadratic because, again, there's 5 terms here, and to make it look like a quadratic, we would need like 3 terms, and there's no way to combine these things. So, I mean, how are we going to figure out what the roots are here? So, go ahead, Julie.
You can split up like the 2x plus 3 as an example, and split them up, and then you make it into like different problems, and then you group from that and have smaller groups.
Oh, that's true. That's true. You could break the 2x plus 3, 2x to the 3rd up. Does that actually work? Did you try it? I was going to say, if you try that and see if it works. I'm not sure. I'll have a different path I want to go down, but I'm curious to see if that works. Yeah.
You could
Megan.
like take the possible zeros and turn them into factors, and then use synthetic division or
Right.
division.
Yeah, exactly right. So, like, what we can do here, right, since we're not really sure what strategy to use, we're kind of at a guess and check, you know. Julie thinks she has maybe an idea about breaking up the thing so we can factor by grouping, and that might work. I don't know. But alternatively, right, this is what we're going to use this rational roots test for. We're going to use these as like a list to guess from, okay? And I am going to guess 1 and see if it works. All right? So we'll use our lead coefficients here. 1, 2, 1, 8, negative 12. Yes! Yes, I know. But that's weird. I was expecting to say, we actually get to do this? But you said it in a weird way. So I don't know why that happened. Maybe I just missed your inflection. Anyway, all right. So we're going to guess 1, a positive 1, as being our possible 0 here. So we'll bring down the 1, right? 1 times 1 is 1, 2 and 1, 3. Did it work for you when you did it?
Yeah.
Oh, okay, cool. I'll have to, that's really neat. What? What are you talking about? I just guessed, but I got it right. Thank goodness. Whew. I hate it when I guess wrong, because then I have to keep guessing. Okay? So that means x minus 1, okay, we could factor this thing with an x minus 1 there. So we'll factor that x minus 1 out. Okay. And that leaves behind then x cubed plus 3x squared plus 4x plus 12. Now, I think your point that you were trying to make earlier too, Cammie, was something we have to be on the lookout for here. But I think we're going to be, again, okay, just because they'll multiply back out to give us that 1x to the fourth. But I'll think back on those exceptions for a later date. Anyway, so at this point, right, now we still have a cubic to worry about. And what should we do from this point? What's that? Ah, right. It looks like grouping might work now. Let's see here. So if I got the x minus 1 and group the x cubed, so I can group out, let's see, an x squared from this first group here. So I'm going to get x squared there. And then that leaves behind, what, an x plus 3. And then the second group, I can factor out a 4. And that also leaves behind an x plus 3. Okay, and so yeah, we're left with x minus 1 times x plus 3. And that leaves us with an x squared plus 4 in the end there. And these are all equal to 0 here. Okay, we also could have kept on guessing if you really wanted to, right? We could have kept guessing here for this polynomial. Okay, our p would still be 12, our q would still be 1. We would still need to consider the same list of zeros, including 1. Positive 1, even though it worked once, could still work again because it's still on the list of our possible zeros here. Okay? But again, since this thing factored, it's much easier to try and factor it with another tool than having to keep guessing and checking because you might be a bad guesser and then you'll be here for a very long time. So anyway, we get x equals 1 then, we get x equals negative 3. We get x squared equals negative 4, and that means this is going to be imaginary. And so we'll keep it rational here with just those two. Okay? Questions on any of that? All right, let's try another one. And then I'll give you guys one to try here after this one. Okay, so far they've been really nice that all those q's have been 1. But sometimes q is not 1. Sometimes q is not 1. Okay. Case in point. All right, so now our p is 8 and our q is 6. And so our fraction, again, the possible zeros will be factors of 8. So 1, 2, 4, 8. And our q, our denominator, is going to be 1, 2, or 3. Or 6. Right, also the 6 too. Okay. Which, I know I say these are the possible zeros, but let me actually list these out, right? Because you might not appreciate the possible zeros just by looking at this. So let me put the list of the possible zeros. Because it's much easier to appreciate when you see it as a bigger list than it is in that kind of form right there. So what are the possible zeros? Well, it's every combination here that's possible, right? So it's 1 over 1, 2 over 1, 4 over 1, 8 over 1. And it's 1 over 2, 2 over 2, but that's the same thing as 1, so we already have that one listed. 4 over 2, that's 2, we already have that one listed. 8 over 2, that's 4, we already have that one listed, so we don't have to worry about it. We have 1 over 3, 2 over 3, 4 over 3, 8 over 3, and we have 1 over 6, so on and so forth here, right? So I'm going to do 1 over 1, that's 1. 2 over 1, that's 2. 4 over 1, that's 4. And 8 over 1, that's 8. But then we're going to do the 1 over the 2's, 2 over 2, 4 over 2, 8 over 2, right? So 1 over 2, that's 1/2. Good times. 2 over 2, that's 1. We already have that. 4 over 2, that's 2. We already have that. And 8 over 2, we already have that. That's 4, right? But then we'll do the 1 over the 3. Now we'll move to our new denominator of 3 there. So plus minus 1/3, 2/3, 4/3, 8/3. Oops, I'm off the screen. There we go. Okay, and then we've got 1 over 6, 2 over 6, but do we need to write that one down? No, because that's 1/3, we already have it. 4 over 6, nope, we got that, it's 2/3. 8 over 6, nope, we've got that, it's 4/3. Okay, so we've got all of our lists there. So you only have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 times 2, 20 things to guess. That's it. Okay, that's all. All right, that's it. Now, of course, sometimes you can help yourself out here. For example, if there's a GCF that you can factor out here, if you can factor out a GCF, that'll lower your P's and Q's by a factor of whatever you factor out. But unfortunately, there is no GCF here, right? It'd be nice if that 17 was even, because then we could factor out a 2, make all those numbers smaller, but nope, 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 nope. Okay. So, again, we're going to guess here. There are tricks, I guess, strategies. There are different little ways you can think, if it has if it changes signs a certain number of times, you can help you figure out kind of different things and stuff like that too. I'm not going to worry about those. All right. If you guys want to learn those or look at them, I'll be happy to tell you about some of them. But we're just going to guess. I'm going to guess 1/2. I'll guess 1/2. Not 1 this time. 1's a good guess. 1's a good guess, but we'll try 1/2. All right. So let's see here. So we've got 6, 17, negative 26, and 8. So we'll drop that 6 down. 6 times 1/2 is 3. 17 and 3 is 20. Half of 20 is 10. And negative 26 and 10 is negative 16. Negative 16 times 1/2 is negative 8. And whew. It's a pretty good guess, Mr. Wibb. Pretty good guess. Okay. Now, of course, what we're looking for here, right, is to have a remainder of 0. If we don't have a remainder of 0, is this a 0 of our polynomial? No, right? So, whew, it's good. Every time we get those zeros. Okay. Might go play the lottery tonight or something like that. We'll see. Okay. So anyway, that means x minus 1/2 is a factor. Okay. And that leaves behind then 6x squared plus 20x minus 16. Okay. But of course there's a GCF we can factor out here. Now there is. What's the GCF we can factor out? A 2. So we'll factor that 2 out. Okay. And now that we're left with a quadratic, do we need to keep guessing? Do we need to keep guessing using our list of possible zeros and stuff? The answer is no, right? Because we know how to factor a quadratic. Or I should say, we know how to factor it if it factors. Okay? Does this thing factor?
Yes.
Yes. Okay, what does it factor to be? Yeah, Megan?
3x minus 2 times x plus 4.
Times x plus 4. Okay. And so that again, we're equal to 0 here this whole time because we're trying to find the zeros, and so we get x equals 1/2, x equals 2/3, and x equals negative 4. Okay. You can imagine here distributing that 2, right? You get 2x minus 1. That'd be the more traditional factor you might see there, but this also is not wrong, right? That is the way you could factor this thing. And so those are our solutions to the original equation there. I guess we wanted to find the zeros. I guess we should set that equal to 0 there. Okay. Those are the solutions then to this equation right there. Okay? So really, it's not about having to find all of the possible zeros. You just need to find enough of the zeros so that you get it down to a quadratic and then factor from there using your normal factoring rules. Of course, keep your eye out for factor by grouping, right? Or any other strategy you might want to use there. GCF, those two. Questions on any of that for me? Yes, Ramike. This right here? So it's you factor like a quadratic, right? So, I mean, do you have a specific strategy you like to use when you're factoring when a is not equal to 1? The magic x thing? Okay, so correct me if I'm wrong here, but you take your magic x, right, and you multiply the 3 and the negative 8, you get negative 24, right? And that goes up here. And then down here is the 10, right? Okay. And so just think of two numbers, right, that multiply to make negative 24, but add to make 10, right? Okay. So that would be negative 12 and positive 2. And you're good from there? Okay. Okay. Other questions? Yes, Miabella?
I was going to say, wouldn't that be 12 and negative 2?
Oops. Yes. Yep, sorry, 12 and negative 2. All right. Other questions, though? Anything else? Good. Okay. Thanks for that, Miabella. All right, so next, then, I'll have you guys try one on your own. Here we go. Okay. Oops. Yeah, go ahead. Find all rational roots of x to the third minus 6x squared plus 11x minus 6. Okay. So go ahead and give them a try. We'll do one more after this. We'll do one more after this here too. Feel working here. I'll give you like 30 more seconds. 30 more seconds here. Okay. 30 more seconds. All right. Jackson, do you have an answer for us? Are you able to find any?
I actually found all three.
Found all three? Okay, what are they?
X equals 3, X equals 2,
X equals 3, X equals 2, X equals 1. 1, 2, 3, 3, 2, 1. That's right. Okay. Questions on any of that? Easy peasy. All right, so then I have, like I said, one more here I want to look at before we cut you loose to get started on your assignment. All right, and that is... we're going to find the real roots of another cubic here, so we'll make it pretty easy, right? If it's a cubic, right, we only need to find 1, 0. Once we find one root or 1, 0 that works, then we'll be able to reduce it to a quadratic, and then we can, factor a quadratic, hopefully. Stuff like that. It's frozen. There it is. Thank you, guys. Okay. So, let's see here. Our possible zeros, right? So it's going to be, oh man, factors of 24, plus or minus 1, plus or minus 2, 3, 4, 6, 8, 12, and 24, all over 1. Okay, so... okay, so only like 16 numbers to guess from here. I'm going to guess 3. All right, so coefficients 1, 7, negative 38, and 24. Okay, drop that 1 down. 1 times 3 is 3, 7 and 3 is 10, 30, negative 8, negative 24. Whew. Okay, and so we've got then, again, we want to see when this is equal to 0, right? So we'll say x cubed, nope, we'll say x minus 3 times, and then what's left over there, the x squared plus 10x minus 8 equals 0. And so now we have the easy part of this, right? We just got to factor x squared plus 10x minus 8. Does it factor? No, it doesn't factor. What should we do at this point then? What's that? Give up?
Do it again.
Do it again?
Like with the x squared plus 10x minus 8.
Oh, you want to, okay, make a new list of possible zeros here, and then, so you're saying like plus minus 1, plus minus 2, plus minus 4, plus minus 8, like that kind of thing? Mm-hmm. Could do that. But here's the thing, right? If it doesn't factor, then those aren't going to help us, right? Because it's got to be able to factor in order for those to be able to help us there. So what do you say there? Quadratic formula. I hate using that. Okay, let's do it though. So negative b, which is negative 10. And Sydney, you're exactly right. I mean, that's exactly what we're going to do. So negative b plus or minus the square root of b squared is 100 minus 4 times a times c all over 2a, 2. Okay, so let's see here. Negative 4, negative 8 make positive 32 with a 100. Root 132 all over 2. Okay, and I think 132, according to what I have from before, it does divide by 4. And so it's going to be plus or minus 2 root 33. Okay, so 132 is divisible by 4. You pull that 4 outside the square, it becomes a 2 over the 2. And so we get that negative 5 plus or minus the square root of 33. Okay. Are these roots, are they rational? Is this rational? The answer is right, is no. These are not rational. But we were asked to find the real roots. Messy underlines there. Okay? There you go. Real roots, real numbers include both rational and irrational. All right? So if the original directions were find all rational roots, we would stop at 3 and say we're done, because when we try to even use the quadratic formula here, we end up with irrational solutions, right? Irrational numbers include square roots that don't simplify any further. All right? But because we said real roots, that includes both rational and irrational, so we're going to include those together. And so x equals 3, and then negative 5 plus root 33, and negative 5 minus root 33. There are our solutions. Okay? And so there's that. So watch your directions, right? If you end up with square roots, and you're only asked for rational roots, you throw out the square root roots, right? They don't count in your solutions. All right? In the meantime, your homework is posted to Google Classroom. If you didn't finish the 10 marks up, you might want to look at that first, right? The 10 marks is due by this evening. So, yep. Check to make sure you can log in. I don't want to get any emails at like 11:30 at night saying, Mr. Witt, can you send me my username and login? I forgot my login. I forgot it. Okay? Also, don't send me an email at 11:30 at night. Mr. Witt, 10 marks isn't working for me.
Send it at 11.
Oh, there you go. Perfect. Yes. Okay, you better check your 10 marks. Make sure it works. And you're done the 10 marks, and let's get those books out and get started on the book assignment then, which is on Google Classroom. It worked? What you finished? Nice. Did you do the homework already? Yeah. Okay. Then. Say again now.
Will you do an antiderivative for me?
I will try. Let me finish the recording here real quick.
Can I write it on the board?
Yes, sure.